Okay, so first topic, limit definition of a derivative. So that's what we did in 3.1 and 3.2, and this was setting up like the limit as h approaches 0. So that's this definition, limit as h approaches 0, and then of all of this. So if you guys remember, we did that in 3.1, and I think we did that in a little bit in 3.2 as well, like actually plugging in, simplifying, calculating all of that out. So we did it the long way for multiple days, and then in 3.3 it was like, oh look, shortcuts. So on the test, you will have to do this once, okay? There will be one time where you definitely have to do it, and I will be very clear. It will say, calculate f prime using the limit definition of a derivative. So if it doesn't tell you, you get to use the shortcuts that we've been using for the last several days, but you will have one problem on tomorrow's test where you have to actually do it the long way and do the limit definition. Okay, so that was the 3.1 stuff. Also in 3.1, we introduced tangent lines, and tangent lines we've been working with throughout. So I want to go through some important points with tangent lines too. And I think I told you guys this yesterday. Eventually, I will have you guys trained that when you read the phrase tangent line, you just immediately write down the point slope, y minus y1, and then m and x minus x1. So this leaves three pieces, like the y you leave, the x you leave, because there should be an x and y in your final equation, but then each of these pieces, like the x1, that's the one that's just going to be handed to you. So that will be given. They'll say, like, find the tangent line at x equals 3, or something like that. So this is given. And then I would jump to this one. How do you find the y1? So you're given the x value, you're given a function. Go ahead. Good. So the given x gets plugged into the original function. So this, we plug this into the original function. So like at this point, all of this could be done without any calculus at all. No calculus is necessary to do what we've done so far. So plugging the x value into the original function, that gives you your y1. And then what about m, the slope?
Plug x into the derivative.
Good. Plug x into the derivative of the original function. And this is something that we emphasized yesterday. Make sure that the slope is a number, not a function. It should not be the derivative function, because that wouldn't be a line. It would be some sort of crazy curve. So that should just be a number. That way it's a line, and tangent lines are supposed to be linear. It's like I should say plug x into the original function, plug x into the derivative function. So whatever is given to you, you'll plug it in to the original, get your y, take the derivative, plug the x into the derivative, and then you have your slope. And I would leave it like this. This is point slope form. I would leave it just like that. There's no need to distribute the slope and add the y over. I would just leave it in that form. I will accept it. The AP test will accept it. So those are tangent lines. You guys will definitely see one or two of those. Okay. I want to make you guys just a big list of all the derivative shortcuts, because then in 3.3 we started with, or in 3.2 we started with basic derivative rules. So we're just going to make a big list of all of the derivatives that you should have memorized for tomorrow. And then we're just going to keep adding onto this list as we go. Okay, so derivative rules. So in 3.2, we had our first two basic derivative rules. The first one we call the power rule, so just x to any power n, and n can be anything, positive, negative, fraction, decimal, irrational number, it does not matter. N just has to be some sort of real number. So we take the derivative, rule goes like this. The old power comes out front as a coefficient, and then we subtract 1 to give us our new power. And then in 3.2 we also had what I call the best derivative ever. What's the derivative of e to the x? E to the x, beautiful. Okay, and then just yesterday we did 6 trig rules. So we've got cosine, sine, tangent, cotangent, secant, and cosecant. Okay, so these were all learned yesterday. I'm just going to write them all down. And you guys have these all somewhere. It's just nice to have them all in one place.
We have to number all of these.
Yes. Okay, so those are the 6 trig functions. Let me show you guys some patterns. So really, like, if you have these 3 memorized, there is a pattern between this one and this one. So these are the original, like this is sine, tangent, secant, and these are all the co-functions. This is cosine, cotangent, cosecant. So first pattern I want you guys to notice is all of the original functions just have positive derivatives. All of the co-functions have negative derivatives. That's the first thing that you can remember, first little trick. And then if you look at the comparison between the two of these, this one's positive, this one's negative, and this is just the negative co-version of this one. This is positive secant, negative cosecant, tangent, cotangent. So these are almost identical. This is just the negative co-version of this one. So if you know this one and you know the pattern, you can get this one. Same thing here. This is positive secant squared. This is negative cosecant squared. Pretty similar. And then this one's positive cosine. This one's negative sine. So this one, it's still the co-function. This one just starts with cosine. So the pattern's a little bit backwards here because these ones are all non-co-functions. These ones are co-functions, and this one's flipped. But these ones, so sine, the derivative is cosine. Derivative of cosine is negative sine. Okay, so all the co-functions have negative derivatives. That's an easy part to remember. Okay, so those are the 8 functions that we know how to take the derivative of so far. And then we have 4 additional rules. We have a sum and difference rule, constant multiple rule, product rule, and quotient rule. So I'm going to write those down just in generic form with like f of x and g of x. Okay, so constant multiple rule. Let's say that you had a constant k and then multiplied by a function. So that constant could be anything as long as it's a number. So the rule says we just kind of hold the constant out front and multiply it by whatever the derivative is. And this is one you guys are probably doing without even really realizing that you're doing it. Okay, next one, sum and difference. Same thing, I guarantee you guys aren't even thinking about this one while you're doing it. Any terms that you have that are added and subtracted, this just says you take the individual derivatives and just keep the signs. So you would take, the derivative of f and then either add or subtract the derivative of g. So these two are happening without you really noticing that you're doing anything. Okay, product rule, quotient rule. Sometimes even like yesterday I reminded you guys at the beginning of class, like don't forget about the product and quotient rule, and some people immediately forgot about it and just did like derivative times derivative or derivative divided by derivative. That was you guys, yeah. You guys did that. So make sure that you are doing the product and quotient rule. Yeah, Eric, I was like, yeah, write down product rule, quotient rule, and you're like, nah. He did, then he did. There you go. All right, so I would do that tomorrow. Write down product rule, quotient rule. Anytime that it's a product that can't be simplified. So let's say if you had like x squared times like 7x to the 5th or something like that, you could simplify that and then just take the derivative. But if you had like 7x to the 5th times sine of x, there's no way that you can simplify that or combine them at all. So that would have to be one function times another function. So if you can algebraically simplify and avoid the product or quotient rule, I would do that. When there's trig or exponential, if it's a combination of different functions. If it's like trig times exponential or trig times algebraic or even trig times trig, because like cosine times sine, you would have to use a product rule as well. Okay, so we've got the first function times the derivative of the second function plus the second function times the derivative of the first function. And remember, the commutative property tells you that multiplication, the order doesn't matter, and addition, the order doesn't matter. So within these terms, I could swap the multiplication and it would stay the same, and I could swap these two terms in order and it would stay the same. You can add or multiply in any order that you want. But these are the basics, is you have to have the derivative of one of them times, ooh, I have that same term twice. You guys, why'd you let me write that? Here we go. It's okay. It's all right. I'll forgive you. Like looking around and all of your faces just looked like confused and sad, and that was because I wrote the exact same term twice. Okay, so first times the derivative of the second, and then the second times the derivative of the first. Okay, so no prime there, just a regular g of x. Okay, do you feel better now? There we go. There it is. Okay, and then quotient rule. Low-D high. Get your Swedish accents right. All right, so we have low-D high, so g times f prime minus high-D low. I guess I've never really met a Swedish person. That just seems like what it would sound like to me. All right, so low-D high minus high-D low all over low-low. So that's the denominator squared. Okay, so those are all your rules. These two, very, very, very important. Make sure that you know those formulas, but make sure that you're paying attention to whether you should be using a product rule or quotient rule, because some people just get so wrapped up in doing their derivatives that they just do f prime times g prime or f prime divided by g prime. That will never, ever, ever happen. You have to use the product rule and quotient rule every time. Okay, so throughout, while I'm giving you guys some things like this, I'm going to give you guys some problems from the book that you should know how to do. And these are problems that you guys did do during class, but just some similar things. So in relation to product and quotient rule, I would write these problems down. I'm going to put them up on the screen so you guys will hopefully remember which ones I'm talking about. So write down those problems so you can look back in the book. Okay, so let me show you what these ones are. We did these all together at the end of class one day last week. So you were presented with a table. You do not have the function. You just had a very finite table of values, just f of 4, f prime, g of 4, and g prime, and then asked to find like generic product rules and quotient rules. So you guys should know how to generically do these rules or combinations of these rules. And you don't have to know what the function is. You just write f prime. Or you just write g prime, and you're just pulling values off of the table. Okay, so know how to do problems like this. We did do these all together in class at some point last week.
We didn't do 39.
We didn't do 39.
42.
Okay, well 39 is actually easier than 40, 41, and 42 because these are more complicated versions. 39 is just a generic product rule and a generic chain rule. Like f times g prime plus g times f prime. Okay, so something like that will definitely be on the test, using your numerical values and doing generic product and quotient rules. Okay, questions on any of this list of derivatives that you guys are supposed to know? Okay, next thing is talking about graphs. So looking at f versus f prime, you guys will also have a matching section, matching a function with its derivative, like you guys had in some of your homework. Okay, so f versus f prime. Let's make a little table here. So f is something, f prime is something. Okay, these are the features I would suggest you look for when you guys are trying to match the original function to its derivative. So if the original function is increasing or decreasing or stopped, you guys should know what those three features should look like on the derivative. So if our original function is increasing, what would you see on that same interval of the derivative? Positive. Good. This would be a positive value. If f is decreasing, f prime is Negative. And by positive and negative, we mean like above the x-axis or below the x-axis. Like positive y values or negative y values. And if f is stopped, f prime is 0. Good. That would be an x-intercept. Okay, so those three features. So again, let me give you something to compare with. Page 141, number 66. This is a matching one that you guys had. So let me throw that up on the screen. You guys remember doing these ones? So you guys will have a section like this. The column on the left will be the original functions. The column on the right will be derivatives. And you guys will have to match. I think I have more than this. I think like 5 or 6. So original functions, derivatives, and you'll have to match them up. Yes, sir?
Will there be any, there's like two like functions like on a graph, and we have to tell which one's the original function? Which one's the derivative?
On one graph, no. It'll be separate columns the way that these are. Okay, so questions on that? Okay, so I would write that down as a reference problem so you know what I'm talking about there. Okay, next topic. You guys will have some application problems. So there will be a big section where all you're doing is just finding the derivative. So using these different basic rules, using product rules and quotient rules. And then you'll have a couple problems that are kind of applications of what the derivative shows us. And for reference there, I want you guys to look at these. So write those down. I will put that up on the board as well. Okay, so these ones, I'm sure they'll look familiar once I get them up there. These sections I think we did like 50 through 56, but 50, 51, and 52 are really good application problems. So 50, find the points on the graph of f of x where the tangent line is horizontal. What does that mean? What does a horizontal tangent line mean? Slope is 0. So how would you solve number 50? Set what equal to 0? The derivative. Good, you'd have to take the derivative first, because if you just set the function equal to 0, that's just going to give you x-intercepts of that function, which doesn't tell you where you'd have horizontal tangent lines. What about 51? Find the points on the graph at which the slope of the tangent line is equal to 4. Set the derivative, good, equal to 4. I'm going to keep bugging you guys on the word it, because on the AP test, if you're writing an explanation and you use the word it, chances are they won't accept that explanation, because you need to refer specifically to the function that you're talking about. What about 52? We've got two functions up there. It says find the values where they have parallel tangent lines.
Put the derivatives equal to each other.
Set the derivatives equal to each other. Good. What do you guys remember about parallel lines from algebra?
Same slope.
Same slope. Good. And slope is now a derivative in our, calculus words. So you take the derivative and set them equal to each other, and then you'd solve for x. So whatever x values where you have the same slope. Okay, so that's what I'm talking about when I say application problems. Another topic that we talked about was differentiability. Points where a function is differentiable versus not differentiable. Okay, so in this section, you'll need a calculator for these. I don't know if you guys remember doing these ones where we like zoomed in using a calculator to a certain point and then distinguish whether or not it was a point of differentiability, and then if it was not differentiable, identifying whether it was a corner, cusp, vertical tangent line, or discontinuity. So I'm gonna give you guys just a quick graph of those. So points that are non-differentiable. Okay, so we have the following. We've got something like this, something like that, okay. So 4 different ways that you could be not differentiable at a certain point. So that would be at this point, at this point, at this point, and then at this point right here. Okay, so they all have names. This one right here is called a corner. Very similar to an absolute value type of shape. And for something to not be differentiable, that means the derivative doesn't exist. And if you guys remember all the way back to day one of derivatives doing that limit definition of a derivative, the reason that the derivative here doesn't exist is because as we come in from the left, this is a negative slope. As we come in from the right, this is a positive slope. And you remember from the limits chapter, if the left limit is not equal to the right limit, then the limit does not exist. So here that would mean the derivative doesn't exist right at that point, because you've got two constant slopes that are coming in and then it just changes immediately when you hit that point. So left different than right, that's a corner, that's why that derivative doesn't exist. This one's called a cusp. Really similar idea to a corner, except these ones are getting steeper and steeper as they move towards that point. So while these ones are just a constant slope on both sides, the cusp is getting steeper and steeper towards negative infinity, steeper towards positive infinity. So still a mismatch from the left and from the right, very similar to a corner. This one is a vertical tangent line. And this graph goes completely vertical just for a moment. If you guys remember from algebra, what's the slope of a vertical line?
0.
Undefined. Good. 0 is horizontal. 0 is horizontal. Vertical is undefined. So it's undefined, so that means the derivative does not exist. And then this is some sort of discontinuity. So any discontinuity would automatically not be differentiable. So that's just one example of a discontinuity. It could also be a hole, an asymptote, or an oscillation. Same discontinuities that you guys had in the previous chapter. So any type of discontinuity would be non-differentiable. Yes, sir?
When we like zoomed in and it looked like a corner, but it turned out to like even out.
Then that is differentiable. So that's why you zoom in, because there were I think there were two that you did back to back. That one you zoomed in, and the more you zoomed in, it really just flattened out and it actually was a smooth curve. And there was one that no matter how far you zoomed in, it still held that corner. So yeah, that's what you guys are going to be doing with the calculator, is doing that whole zoom in sort of thing. One more idea with differentiability is that differentiability implies continuity. And that's a really important idea. In the future, when you guys are doing AP problems, they'll just tell you like, this function is differentiable. And if you know it's differentiable, you automatically know that it's continuous. Because a function can't possibly be differentiable without automatically being continuous. What about the reverse? If something is continuous, does that immediately imply that it's also differentiable? No, look at these three right here. These three are perfectly continuous, but they're not differentiable at one of the points in their domain. So if something is differentiable, then it is continuous, and the logic works backwards. If something's not continuous, then it's not differentiable. And that's what comes in with this last category. So if you know something's not continuous, it can't possibly be differentiable, because if it was differentiable, it would be continuous, because of the forward implication there. Okay, so that'll be important, especially in the future, but just know that something being differentiable automatically means it's continuous. Okay, a couple more categories here. Next thing we did was 3.5, which was our higher order derivatives. So second derivatives, third derivatives. Higher order derivatives are basically just taking the derivative again. If you can take the derivative once, chances are you can take the derivative 2 or 3 times. So some patterns that I want to tell you guys about. And these are things we talked about in 3.5. Okay, so polynomials. Polynomials where you have something like x to the n. So a polynomial specifically has to be a whole number power. So like square roots are not polynomials, rational functions are not polynomials. So let's start with something like, I don't know, x to the 4th. Make it a nice simple polynomial. What's the first derivative of x to the 4th? 4x cubed. What's the derivative of that? 12x squared. Good. Derivative of that? 24x. And then? And then? And then? 0. Yeah, the zeros just keep going. Once you get to the zeros, the derivative of 0 is just 0 over and over and over and over again. So polynomials, eventually, they will go to 0. You will get to the point where the derivative will be 0. So eventually all polynomials will go to 0. Now again, remember polynomials are whole number powers, positive integer powers. If it was a negative number, it wouldn't go to 0 because the powers just get more and more negative. If it was a fraction power, it would not go to 0. So it's only whole number integer powers that will eventually go down to 0. Another pattern. E to the x. I could ask you what the 243rd derivative of e to the x is, and what would you tell me? E to the x, good. E to the x is just always, always e to the x. So it's just its own derivative over and over and over again. So which means it's its own second derivative, it's its own third derivative. And then the last pattern is our trig functions. Cosine and sine. Okay, let's start with sine. What's the derivative of sine? Cosine. Okay, so the first derivative of sine is cosine. What's the derivative of that? Negative sine. Good, that's the second derivative. What's the derivative of that? Negative cosine. Good, the negative sign stays, and the derivative sign is cosine. And what's the derivative of that? Positive sine. And we're back. It goes in a cycle. We've got a cycle of 4. What about cosine? Start with cosine. What's the first derivative of cosine? Good. What's the derivative of that? Good. Derivative of that? Positive sine. Derivative of that? Positive cosine. Good. And we're back. So it goes in a cycle of 4. So each of them have cycles of 4. And once you get through 4, then they repeat. So if I asked you what the fourth derivative of cosine is, what's the fourth derivative of cosine? Cosine. What's the 16th derivative of sine? Sine. Good. So they go in cycles of 4 like that. So you should also be able to figure out what like the 17th derivative would be because you know what the first derivative would be. So you can follow that pattern. Okay, last thing. Rates of change in particle motion. So our last section, 3-4. Well, 3-6 we already covered earlier. So rates of change and then particle motion. So rates of change were 3-4. And I just want to refer you guys to the 3.4 day 1 AP problems. I will show you what those were in the notes really quickly. This one. Water tank at Camp Newton, we've got 2 different functions. One is the rate at which water is being pumped in. One is the rate at which water is being removed. Do you guys remember this one? Okay, so you guys should be able to answer a question like that. Given an incoming rate and an outgoing rate, you should be able to answer, you know, is it increasing, is it decreasing at a certain time? So know how to do something like that. That's one reference. All right, last topic is particle motion. Position, velocity, and acceleration. Yes, and that is why I cut it into 2 tests. That would be a really insane test. Okay, so particle motion, the worksheet that we did, was that just Tuesday that we did that worksheet? I think so. Yeah, Tuesday's worksheet. So I'm going to do something really similar to that worksheet. I'm going to give you guys a graph and ask you a whole bunch of questions about the graph. Make sure you know whether it's a velocity or position graph. It will be marked. Just make sure that you're answering accordingly. So here, just a sample of questions that I could ask you about that. Actually, let me write, I'm sorry, one thing. S of t is position. V of t is velocity, which is the derivative of position. And then A of t is acceleration. It's the first derivative of velocity, which makes it the second derivative of position. Okay, so now a sampling of things that I could ask you. I could ask you when the particle is moving forward or moving backward. And if we use that worksheet as a reference, Tuesday's worksheet is going to be great for helping you guys study for this part of it. So moving forward or moving backward? Moving forward means velocity is positive. Moving backwards means velocity is negative. And again, by positive and negative, we mean above the x-axis, below the x-axis. What about changing direction? Nick, what do you think? Good, crosses through the x-axis. Good, so an x-intercept that actually does have a change in sign, because it is possible to have an x-intercept that goes right back the same way, so make sure it actually crosses through. So this would be where we crosses through the axis, or you could say that v changes sign. So whatever you have for the velocity. And the answer that it crosses through the axis, that's assuming we're looking at a velocity graph. It would be slightly different if we were looking at a position graph. Changing direction, so cross through the axis of a velocity graph, or you could say that velocity changes sign. All right, last thing, speeding up and slowing down. Okay, they could each happen two different ways. Speeding up could happen if velocity was positive and increasing, or if velocity was negative and decreasing. So remember when we say speeding up, we want to know if the speed is increasing or if the speed is decreasing, and speed is the absolute value of velocity. So for the first one makes sense. If the velocity is positive and increasing, it's getting faster and faster and faster. And here, if our velocity is negative and decreasing, that means it's getting more and more negative. So if it's getting farther away from zero, that actually means it's speeding up, because speed always takes the absolute value. So either already positive and just getting more positive, or already negative and getting more negative. And then slowing down is the opposite. Slowing down would be if the velocity was positive and decreasing. So that means it's above zero but headed back towards zero, or negative and increasing. So that would mean you're below zero but headed back up towards zero. Basically, just think of whether you're headed closer to a velocity of zero or farther away from a velocity of zero. Closer to a velocity of zero would be these two situations, slowing down. Getting farther away from a velocity of zero would be speeding up. Okay, that's all I have for you. Do you guys have any questions for me? Okay, so